Hello everyone, welcome to session 6. In this session, we shall see concept learning as a search and findest algorithm. So in the previous session, we have discussed what do you mean by concept learning and also inductive learning hypothesis. Now, the thing is, here the concept learning can be viewed as the task of searching through large space of hypothesis that is implicitly defined by the hypothesis representations. And the goal of this search is to find the hypothesis that could best fits the training examples. And also it is very important for us to note that by selecting a hypothesis representation, the designer of the learning algorithm that will implicitly defines the space of all the hypotheses where the program can ever represent and therefore that can ever learn. So we shall see the example on this and discuss in detail about the concept learning. So before getting into the example, here we need to find an hypothesis space where it consists of all the set of hypotheses. We need to identify a hypothesis that could be the best fit hypothesis for your instances. So in order to find that, we have to make sure that how much hypotheses are there in your hypothesis space. Let's consider an example here. As you know that in the enjoy sports learning task, there are 6 attributes are there. So the first attribute is sky, which is having 3 values, and remaining attribute has 2 values each. So in order to identify distinct instances, you compute these values. 3 is nothing but your sky's 3 different attribute values. These 2 values are air temperature, humidity, wind, water, and forecast. So when you compute this, you will find 96 distinct instances. Similarly, when you compute by using 2 more values, that is along with your 3 different values of sky attribute plus distinct, that is constraint, that is question mark, any value is acceptable, plus null value. So totally 5 different values are there. And similarly for remaining attributes also, here 4 you will get by taking 2 values of your attributes and remaining question mark and null values. So if we compute this, you will get 5120 syntactically distinct hypothesis in your H. So in this H, you will have 5120 syntactically distinct hypothesis. So every hypothesis contains one or more null value symbol or null value, so which represent the empty set of instance, so which classifies every instance as negative. So if you consider this statement and compute, you will find 973 semantically distinct hypothesis. This one is for to make your every instance as a negative instance by taking your null values. And these 4 values are 3 values with respect to your sky attributes values and another is your question mark. Similarly for this one, 2 values for your air temperature plus any values acceptable constraint. So when you compute this, you will find 973 semantically distinct hypothesis. So let's consider the next topic is general to specific ordering of hypothesis. So here we will learn a relationship called as more general than or equal to relationship between your hypothesis. So there are many algorithms out there for your concept learning, so that will organize the search through the hypothesis space that depends upon a useful structure, so that may exist for any concept problem like your a general to specific ordering of hypothesis. So by taking that structure over the hypothesis space, we can design learning algorithm that exhaustively search even infinite hypothesis space without explicitly enumerating every hypothesis. So to illustrate this general to specific ordering, let's consider two hypotheses, that is H1 and H2. When you compare H1 and H2, you can see H2 has fewer constraints on the instances, and when you have H1 you can see more constraints than H2, because Sunny, there is only one constraint that is applicable for attribute 1, whereas in H1 you can see two different values for two attributes, and the remaining attributes values that you can see there as a any value is acceptable constraint, which means that any of the instances, that is x1, x2, x3, see, assume that these are the three instances, which makes your H1 as a positive hypothesis, which means if H1 classifies your x1, x2, x3 as a positive instances, obviously your H2 will also classify H1, H2, H3 as a positive instances, because you can see that the constraints on H2 is lesser than your H1. So we can say that H2 is more general than or equal to H1. Now we can define the more general than or equal to relation in terms of set of instances that satisfy the two hypotheses. So let's consider two hypotheses, that is Hj and Hk, where Hj is more general than or equal to Hk if and only if any instances that satisfies Hk that also satisfies Hj. You can see the definition over here. The definition: let Hj and Hk be the Boolean valued function which is defined over X, that is set of instances. Then Hj is more than general than or equal to Hk if and only if the condition is given. The condition is if Hk satisfies on a particular instances that also satisfied by your Hj, which can also be written as Hj is greater than or equal to Hk, that is more general than or equal to relationship. So in this figure you can see here, in the leftmost thing you have a set of instances, and the rightmost you have a set of hypotheses, and also you can see the arrow marks here, that is showing the relationship of hypothesis on instances, and also here there is an arrow mark which is moving upward direction, that is from H2 to H1, which says that H2 is more general than H1. And also you can see these notations also. Let's consider an example here. Let's we have x1 as an instance, x2 is another instance. When I have H1 which is having some sort of constraints on attribute values, your Sunny is there, and any value is acceptable, strong, any value is acceptable. I need to check whether my hypothesis is consistent or satisfies with respect to x1. You can see here Sunny, here warm, any value is acceptable. Here also high is there, any value is acceptable. Strong is there. Cool and same, here also any value is acceptable, which means that H1 satisfies x1, whether it's a positive instances or negative instances, it doesn't matter, but H1 of x1 is equals to 1. Now let's consider with the same example with x2 with respect to H1. Sunny is there, warm, any value is acceptable, high, any value is acceptable, Here we have light and we have strong, which means that H1 is not satisfying your X2, which means that you can write it as H1 of X2 is equals to 0. Here you can see the notations. H1 is satisfying only X1, not with X2. So the similar way with respect to H2 and H3. In this diagram, it is mentioned clearly that how and each and every instances in your instance set is satisfied by the hypothesis in a hypothesis space. And also you can see the relationship called as more general than or equal to relationship. So with this basic information on concept learning as a search, where we have studied a hypothesis space and how many distinct hypotheses are there with respect to semantically and syntactically, and distinct instances are there, and also we have seen the general to specific ordering of hypothesis and more general than or equal to relationship between the hypotheses. So with the help of these information, now let's discuss an algorithm called as find S algorithm. What do you mean by find S algorithm? That is, you need to find an hypothesis which is maximally specific. Here we have 3 steps are there with respect to the find S algorithm. The first step is you need to initialize an hypothesis which is most specific hypothesis. How do you represent most specific hypothesis? By placing the attribute value with the null constraint. So when you place these attribute values with the null value, then we say that it is most specific hypothesis. We have placed only 6 values because we have taken an example called as enjoy sports concept learning, where we have only 6 attributes. So the hypothesis is represented with the help of null values for all the attribute value. This is first thing. Second step is for each of the positive training instances, that is X. Remember, find S algorithm will consider only the positive instances, not negative instances. Whenever the negative instances occurs, it will reject that negative instances and it will consider the next possible positive instances. So in the second step, you need to have, means you need to check whether the attribute constraints in H is consistent or not, means that is whether it satisfies with X or not. If it is satisfies, then don't do anything. If it is not satisfies, then you need to replace the attribute value in H, by next more general constraint that is satisfied by the X. See here, in the X you have different values are there with respect to attributes A1, A2, A3, A4, A5 and A6. Assume that these are the attributes are there, attribute values of this particular instance. Let's consider it as a X1. So what this statement says, if the constraint AI is satisfied by X, that is, if these two are satisfied, then you are not supposed to do anything. If these two are not satisfied, then you have to replace the value in the updating hypothesis by more general constraint. That is, here you can replace with the more general constraints. So this you have to repeat for all the attributes and with all the instances, that is only with respect to positive instances. So finally after completion of all the instances, you will get one hypothesis. That hypothesis is called as maximally specific hypothesis. Let's consider an example and discuss in detail how this algorithm works. So to illustrate this finders algorithm, we have taken an enjoy sports task, which assumes that learner is given the sequence of training examples from this enjoy sports task. You can see here there are 4 instances are there: x1, x2, x3 and x4. How many attributes are there? 6 attributes: sky, air temperature, humidity, wind, water, forecast. And the last attribute is to make sure that whether this instance is a positive instance or negative instance. If here you can see the target concept is your enjoy sports. If the target concept is yes, then it is positive instance. If the target concept value, that is enjoy sport, if it is no, then it is a negative instance. So here we have 3 positive instances and 1 negative instance. And we shall start with the first step now. So the first step is to initialize H to the most specific hypothesis in H. This is how we have denoted. That is H, which consists of all the null values of your attribute values. So this is your first step. Second step is, when you have an positive instance, you can see here x1 as a positive instance, you need to compare attribute by attribute with H for a given instance, and you need to update the next hypothesis by replacing with the most general value. So you can see here we have sunny and you have null value. When we compare these two things, it is not satisfying. So what we have to do, you have to replace with more general value than your current hypothesis values. So here I replace with the actual value, sunny. As you know that there are 3 constraints are there. One is any value is acceptable, actual value and null value. When I compare null value with the value, here the value is more general than null value. When I compare the value with the question mark, then we say that more general is question mark, that is value is less general than your question mark. So the concept is here, I need to replace with the more general constraint. What do you have here? You have sunny and you have null value, which is having the more general constraint, that is sunny. So I have replaced with the sunny, and you compare with the next attribute, strong and null value, warm and same. So when you compare this, all are replaced with the values that is more general than your previous hypothesis values. So here I can write as warm, normal, strong, warm and same. This is my current hypothesis. So when I consider the next instance, I need to compare with the previous hypothesis, that is with H1. If it is same, that is if it is satisfying, then in the next updating hypothesis you need not to replace. If it is only when you have the different values, or sorry, if you have the values are not satisfying, then you need to update with the next most general constraint. So what do you have? You have sunny here. Sunny is there in the instance, so you keep the same value in the next hypothesis value. Warm also same, but you have high and normal. So when you have these types of situation, this is considered as a value constraint. Okay, value constraint. So what you need to replace in the next hypothesis attribute value, you need to replace with the more general value. So when you have value, you need to replace with the more, that is a question mark. So strong is there, strong, warm, and same is there, same. So this is how we are done with H2. Now we shall consider the next instance, that is x3. So here when you consider the next instance, that is x3, which is of negative, so as the algorithm says that it has to consider only the positive instance. What we have here, negative instance, so this instances is not considered for your computation. So what we have to do, you have to update your hypothesis by H3 by keeping the same values. So sunny, warm, any value is acceptable, strong, warm, and same. So this is your updated hypothesis with respect to your x3. Here we have not considered x3, but we have to update your hypothesis. And again you have to update your current hypothesis, because still we have one more instance, that is x4. So the updating hypothesis is sunny same. When you have same, don't do anything, you keep as it is. Warm also same. So when you have high and strong, you see there are two constraints are there. One is actual value is there, and more, that is any value is acceptable. When you compare these two things, which is more general constraint is there, this is your more general constraint, so keep that value. So next strong, you have the same value, but whereas your cool and warm, these are the two different values, but it belongs to second constraint, that is value constraint. So you need to replace with the next more general constraint, that is any value is acceptable. Here also any value is acceptable. So right now this is your hypothesis. Whether this is a maximally specific hypothesis, yes, this is your maximally specific hypothesis, because here we don't have any next higher instances. This is your final, and you need to check whether this hypothesis classifies positive instance as a positive, negative instances as a negative instances. So here when you compare H4 with your x3, check that whether it classifies negative as a negative instance. Here you have sunny, and whereas you have rainy here. So this does not satisfy. It means that H4 is classifying x3 as negative instance. So this is this H4 is your final, that is maximally specific hypothesis. So in this figure, you can see that the hypothesis space search is performed by Finder's algorithm. So here the search begins with H0, that is with most specific hypothesis in H. Then by considering your hypothesis, that is H1 through H4, based upon your training examples. In the instance space diagram, positive training examples are denoted with the plus symbol and negative by minus symbol, and the instances that do not being present as a training examples are denoted by solid circles. So this figure will illustrate the search in terms of instances and hypothesis space. At each step, the hypothesis is generalized only as far as necessary to cover the new positive examples. So at each stage, the hypothesis is most specific, consistent, with the training examples which is observed up to the last point. Here you can see some of the key properties of finder's algorithm. The first one is the finder's algorithm will guarantee to output the most specific hypothesis within hypothesis space that is consistent with the positive training examples. The second property is finder's algorithm, that's final hypothesis will also be consistent with the negative examples provided the correct target concept is contained in hypothesis space and provided the training examples which are correct. So these are the two key properties of finder's algorithm. So let's see, there are some of the questions which are unanswered by your finder's algorithm. The first one is whether the learner converges to the correct target concept. Here, the finder's algorithm will try to find an hypothesis which is consistent with the training data. It has no way to determine whether it has found the only hypothesis in H that is consistent with the data, or whether there are many consistent hypotheses as well. So the next question is why we need to prefer the most specific hypothesis. So in this there may be the multiple hypotheses which are consistent with the training examples, but finders will find the most specific. So it is unclear whether we should prefer these hypothesis space over the most general or some other hypothesis of intermediary. And the third one is, are the training examples are consistent? So in the most of the learning problems, there is some chances that a training example will contain at least some error or noise. So such inconsistent sets of training examples can mislead your finder's algorithm. So given that the fact is it may ignore negative example. So we would prefer an algorithm that could be least detect when the training data is inconsistent, that can accommodate such errors. And the last one is what if there are several maximally specific consistent hypotheses? So these are the some of the unanswered by the finder's algorithm. So this completes the session. So we shall see in the next session on version space and the candidate elevation algorithm. Thank you so much.